Okay, so as you saw from lab 3, if we apply a force to an object, that object can accelerate. And as you saw from lab number 4, if we add up a bunch of forces together, the net force tells us what the object is going to do. And we introduce that as Newton's second law, and Newton's second law states that the net force acting on an object equals the object's mass multiplied by its acceleration. Somebody pointed out to me yesterday, he said, well, isn't force just equal to mass times acceleration? And the answer is no. I'm not saying that you can't use that relationship. It's just understand what the relationship is saying. That a force will cause a mass to accelerate. So you can see how the equation turns into a sentence. Okay? So the next question then is, since we now know how to calculate the net force, how can we use that to find the acceleration? Okay, here's a simple problem. An airplane touches down on a runway. The airplane lands with a speed of 33.5 meters per second and takes 9.57 seconds to come to a stop. If the mass of the airplane is 850 kilograms, what is the net braking force? All right, so you can visualize this airplane touching down, and then all of a sudden the engines reverse, the thrust reversers come on, the brakes come on, whatever it is that brings this airplane to a stop. Now, this is not exactly finding acceleration from the forces. What this actually is finding the force from the acceleration. You guys see that? See, first step we're going to do is we're going to draw the picture, and there's my picture. There's my airplane. Now, in this case, I'm going to use two pictures. The first picture is the airplane when it touches down, where we have some information on. And then the second picture is when the airplane comes to a stop. And as you can see, the airplane is going to take some distance to come to a stop. I could certainly put in a bunch of labels, not the least of which is how far does the airplane take to land, which, a little bit of an aside, is kind of an important thing to know. You want to make sure that your landing distance is shorter than your runway. Otherwise, you've got yourself an ATV airplane, and that's not a good thing. Okay? But what are we given in the problem? We are given the initial velocity, and we're given the final velocity. Since we see, in this case, the initial velocity is pointing to the right, the final velocity is 0, so that means the velocity must be slowing down, it must be coming to a stop. The direction of the acceleration must be opposite the direction of the velocity. All good here, right? Okay, so we know V0, we know VF, we know the mass of the airplane, and we know the time it takes to come to a stop. We do not know the acceleration A, so in my table of variables, there's my table of knowns, V0, VF, delta T, M. We do not know A, we do not know the braking force F. Okay? So far so good? What is the physical relationship then? There's two physical concepts we can apply. The first one is that Newton's second law applies. That is to say that the braking force is going to cause the mass to accelerate. F equals ma. Of course, we don't know what A is. So that means we got to go to the next one, which is the definition of acceleration. And the definition of acceleration, of course, is the change in the velocity divided by the time interval. Do we know what the change in the velocity is? Yes, we do. So we write our two equations based on those principles. F equals ma, in this case the net force equals the mass of the airplane times its acceleration, and A equals Vf minus Vi over delta T. All good? And so what we see is we can plug our values into the second equation to find a value for A, and then we can take that value for A, plug it into the first equation to find a value for F. Very easy, isn't it? Okay. Okay, so what we end up getting is when we plug it in, we get a braking acceleration of negative 3.5 meters per second squared. We then go plug it into the net force equation and come up with a force of negative 2.98 times 10 to the third newtons. Okay, so you see where that you see how that works out. Now we can do this the other way around though. What we did here is we found the acceleration to find the net force. What if I give you a bunch of forces and you need to find the acceleration? Then we have to go back to what we did in the previous hour. Find the net force, take the vector sum of all the forces to find the net force, set that equal to mass times acceleration, and then find the acceleration. Okay? Want an example of that? Here's an example of that. A 25, now this is a little bit different, not necessarily the way I described it there, but we can work this particular problem. If 25 newtons makes an object accelerate at 3.5 meters per second squared, how much force must be added and in what direction to make the object accelerate at 2.25 meters per second squared? Go ahead and work together on this one. I'll give you a few minutes to work on it. All right, what we're going to apply is we're going to apply Newton's second law. Newton's second law says that the net force acting on the cart is going to be equal to the cart's mass times its acceleration. Now, net force means sum of the forces. The only forces we're worried about is the forces that are pushing or pulling it. Let's just go ahead and say that the up and down forces cancel each other out. We don't have to worry about it. Okay? Then in the first case, where we have the first force causing the first acceleration, we could write F1 equals m times A1. You with me here? Okay. Now in the second case, we're still applying F1, but now we're going to apply a second force, F2, which will now cause a new acceleration. Now I'm not saying we're getting rid of F1, it's F1 and F2 combined are going to give us our new acceleration, A2. You with me there? Okay. Now, all I got to do, I take a look at this and I see two equations and two unknowns again. I don't know m and I don't know F2. Well, good news, everybody. This one's easy. All I have to do is solve each of those equations for mass and set them equal to each other. And so I get the proportion F1 to A1 equals F1 plus F2 to A2. Net force divided by acceleration is going to be equal to the net force divided by the acceleration. Because it's the same cart, the mass doesn't change. Do you see how we can work with that? Okay, then all I've got to do is a little bit of algebra. You see the algebra here, right? First we got to do the cross multiply, then we got to get rid of the common factors. First we get rid of the A2, multiply both sides by A2, then we subtract out F1, and that gives us our expression for F2, the force we're going to add on. When we get finished, it gets negative 8.93. That means we have to, if we're applying the original force to the right, then this force must be applied to the left. Does that make sense if we're going to have a lower acceleration? It does make sense. Okay, great. It's a retarding force. It's a force that's going to decrease the rate of acceleration. Not bad, right? Okay, now comes the fun one. See, that was an example of using F equals ma by using the ratios. Now what happens if I give you a problem where you have to find the forces and you need to find the acceleration? A car is on an 18-degree slope. Please find the acceleration as the car rolls downhill if it has a mass of 650 kilograms. This one's going to be a little bit more interesting, isn't it? What do you think is the first thing, after we read it, what are we going to do? Draw a diagram. There's the diagram. Okay, guys, let's go ahead and get started. I would suggest you do a free body diagram of the cart and then use that to find the net force. Looking around at your work, we have a couple of issues. First of which is you guys still need to figure out how to do your free body diagrams correctly. Okay, that's all right. We're going to learn from it. First off, what are the objects interacting with the cart? There are two things interacting with the cart. The earth is one, and the ramp or the hill surface is the other. And so we end up getting weight pulling it straight downward, and the normal force provided by the hill, the support force provided by the hill, pushing up and to the right. Okay? No other forces. There's no downhill force. How do I know there's no downhill force? Because there's nothing else that the cart interacts with. If you don't have an object providing the force, you do not have a force. Okay, oh, by the way, some of you may have thought friction, and that would be reasonable, but we're going to take friction out of this particular problem by having it roll without sliding, so we're okay there. Okay, one more detail. What is the object doing is accelerating. And as you notice, my acceleration vector is green and my force vectors are red. The reason being, I can't add an acceleration vector to a force vector. I don't want to mix them up. Okay? Also notice when I draw my free body diagram that I have them originate from the same point. They're both, these are the forces acting on the cart. The hill's pushing the cart up and to the right. The earth is pulling the car down straight away. Now what we want to do is we want to find the net force. The net force is simply the sum of the forces. So that would mean I would take a weight, there's my weight vector pulling downward like this. I'm going to add to that my normal force, which is pushing up like this. And then that means that this line right here represents the net force. So you see how that works out? I don't end up back at the starting point. Okay, so how does it work? Well, we're going to play a little cheat here. The cheat goes this way. I get to choose the coordinate axes. You see, if I have it like this, and I use our standard coordinate axes, x to the left or x to the right and y up, then w would only have a y component, but n would have an x and a y component, and the acceleration would have an x and a y component as well. Well, I could then still find the acceleration by using Pythagorean theorem, but let's pull a little trick. I'm going to choose my x-axis to be the direction of the acceleration. If I do that, then my acceleration is only going to have one component, the x component. See how that's going to make it a little bit easier? The only thing I have to do then is I have to have my y-axis perpendicular to my x-axis. In this case, the y-axis ends up being perpendicular to the slope. You following along with me, guys? This is a little math trick when we're dealing with slopes. I always do this. Whenever I know which way the acceleration is going, I choose that direction to be my x-axis. That way I only have one equation for my acceleration. Nice little trick there, yes? Okay. All right, so that would mean that A does not have a y component, and N does not have an x component. That makes it a little bit easier. But what about W? Now W does have an x and a y component. So W has to be calculated out. I have to figure out Wy and Wx. Okay? Do you see what I mean? I have a component of my weight which is going to pull the cart down the hill, and I have a component of the weight which is pulling the cart into the hill. Do you guys see that now? Now you see what's driving the cart. It's the component of the weight that's pulling it down the hill. Okay, one more little detail. How do I know that that's the angle theta? Well, let's say I go ahead and draw my standard orientation. So there's my x, and this is my y. Okay? What did I have to do to go from here to here? I have to rotate that angle theta, yes? Because I have to rotate this by that angle theta. Well, if I do that, I've got to rotate from here to there. There's the angle theta, so there's my angle theta in there. You following along with me, guys? A little geometry proof there. I can't even remember the name of that proof, but you can see what I'm talking about. Okay, so Wy becomes adjacent to theta, so therefore you have to use the cosine for Wy, and Wx becomes opposite, so you have to use the sine to find Wx. That's a little different than what we're used to, yes? That's why we want to look at the triangle. We actually have to see the triangle. Okay, now there's one more little detail. In order to find the weight of the object, We need to find out what the force of gravity is pulling on it. How do I calculate the weight of an object if I know its mass? No. How do I calculate the weight of the object if I know its mass? The weight is equal to what? Come on, guys. It was in the reading, and it's in the lab book, and it was also in your high school physics classes. M times, so what is, weight is equal to mass times? Wrong. It is not equal to mass times gravity. Weight or gravity is not equal to mass times gravity. What are my units of G? No. Come on, guys. You're telling me weight is equal to m times g, or mass times gravity. So what are my units? What is g? G is what? 9.8 what? 9.8 meters per second squared. Wait a minute. What does that measure? An acceleration. That's why I set you guys up. I have to unteach a habit. You guys have had this pounded in your head in high school that weight is equal to mass times gravity. Gravity is a force. Gravity is measured in newtons. Gravity is weight. G, which you guys have learned, is 9.8 meters per second squared. That's an acceleration, guys. Meters per second squared is an acceleration. So it is not mass times gravity. It is mass times the free fall acceleration. And you're going to hear me say that over and over and over again. Mass times the free fall acceleration. Again, it's not that you guys did anything wrong. It's just I have to unteach some bad habits. You following along, guys? And that's the reason why I have it written the way it is. It's not mg sine theta and mg cosine theta. It's m a sub g, mass times the acceleration due to gravity times the sine of the angle. And mass times the acceleration due to gravity times the cosine of the angle. You following along, guys? You see what I'm talking about? We're looking at accelerations here. Now, the value of that acceleration is 9.8 meters per second squared. Okay? But every time you guys say that weight is equal to mass times gravity, I'm going to figuratively beat you up. Okay? All right, cool. Why is this important? Not that part. Why do we need to do all this? Because now we have a Wx component and now we have the Wy component. That means that our equation becomes the normal force plus the weight equals the mass times the acceleration. The vector sum, n plus w equals ma. Okay, that's my vector equation. The next step is to write my component equation. My component equation is nx ny plus wx wy equals max may. Okay, all good. Now we need to replace each of those with the components. Just a little reminder here, and I'm going to do a quick sketch here. There's the cart. Okay, here's my normal force pushing this way. Here's my weight pulling down this way. Oh, wait a minute. That's why I feel weird. There's the weight pulling down this way. So here's Wx or Wy. Here's Wx. There's the acceleration A. Positive x downslope, positive y perpendicular to the slope. And now you can see that the x component of the normal is going to be 0, and the y component of the normal is just the magnitude of the normal. The x component of the acceleration is the acceleration, the y component of the acceleration is 0. That leaves us the components for wx and wy, so it's m a sub g sine theta for x, and minus m a sub g cosine theta for y. Now, why is that minus? Negative direction with respect to what? Well, I mean, take a look at the other y force. The other y force is the normal force, yes? So if the normal force is pointing up is positive, then the weight must, because it's pointing down, must be negative. That's all it is. Use the diagram to assign the sign. Now we've got two equations. Well, do we need two equations? What's the question asking for again? The acceleration. So let's go ahead and take a look at the top equation. MAG sine theta equals MA. How many unknowns do I have in here? Just the one, just the acceleration. Oh, by the way, a miracle happens here. This is the reason why I don't want you to put in numbers right away. Because if you put in numbers right away, would you see something here? What can we do? Cancel out the mass. We can't cancel out A. Those are two different accelerations. A is the acceleration down slope. A sub g is the free fall acceleration. But we can cancel out the mass. And so we get the expression A is equal to A sub g times the sine of the angle, which means we don't care if the car is empty, full, or even a roller skate. Everything is going to have the same acceleration as it goes down the hill. You following along here, guys? This is why you see on any sporting event that involves going down a hill, why everything is so close to each other, why all the speeds are so close to each other. The only difference is who can reduce the frictional forces the most. Okay? The weight does not, the mass does not matter. Plug in the numbers and we get around 3 meters per second squared. You following along, guys? Again, the method. Draw the picture. Identify the object of interest. Draw the free body diagram for the object of interest. Then, using Newton's second law, net force equals mass times acceleration. The free body diagram tells you the forces that you have to add up. Once you write the vector equation, you then have to write the component equation. Okay? And then from the component equations, you can then solve for the unknowns. Now let me do one more particular problem. It's not hard. We're not even going to break for it. What I'm going to do is I'm going to take this same problem. The car is on an 18-degree slope. Find the acceleration as it rolls downhill if it masses 650 kilograms. I'm reminded of a really bad joke from a comedian, Mitch Hedberg, who said, "I drove 3 miles with the parking brake on." It doesn't say much for me, but it says even more for the parking brake. Okay, so my question for you is this. What's the acceleration if somebody left a brake on? There's the brake. 150 newtons of force is being applied. All right, what does the diagram look like? Does the picture look any different? Well, it does have a difference. What is that difference? There's going to be a braking force. Which way is it pointing? Upslope, exactly right. So there's the braking force, upslope. Does that change your vector equation? Yes, it does. Not the principle behind it. The principle behind it's still the same. Net force equals mass times acceleration. But now we change the vector equation because now we have an additional force. It now becomes FB plus N plus W equals MA. So you see, all we're doing is we're just adding one more vector. Then the next step is if we added one more vector, we've got to break it up into components. Well, I made life a little easy. Does it have a y component? Look at the direction of the xy axis and compare FB to it. Does FB have a y component? No, it does not. FB is strictly in the negative x direction, isn't it? So that makes the component equation very easy. We just add another column, FBY and FBX. We then replace FBX with negative FB, and FBY gets replaced with 0, so it's still the same. It's still a similar equation, isn't it? Let's go across the top. We go across the top and we see minus FB plus MAG sine theta equals MA. After a while, you're going to learn to read equations. What we see here is a component of gravity is pulling downslope, but the brake is pushing back upslope, and we're going to have a net acceleration downslope, one hopes. By the way, a little bit of an aside. If my answer turned out to be, if my acceleration turned out to be negative, does that make sense? No, it does not. Because that would mean, now only, well, let me backtrack. It would make sense only if the cart was rolling to begin with. If the cart was starting from rest and we had a negative acceleration, we can't have it accelerate upslope. Do you see what I mean? So sometimes you have to take a look at your answer and go, does this make physical sense? Okay, well, the good news is when I plug in the numbers, I come up with 2.8 meters per second squared. One more little detail. In the fourth line, minus FB plus MAG sine theta equals MA, can I cancel out the mass? No, I cannot. Because while I've got a mass term, or got a mass factor in the right-hand side, and a mass factor in the second term of the right-hand side, or excuse me, second term of the left-hand side, I do not have a mass factor in the first term. So while I can divide FB by the mass, I cannot cancel out the mass completely. So in this case, the mass of the vehicle does enter into the game physically. If it's a big, massive object, the brake is not going to have that much of an effect on it. If it's a relatively small thing, the brake could have a large effect on it. See where we're going here, guys? So you can see how I can take these equations and actually interpret them into a physical action. Although it certainly helps to have the diagram, because when you have the diagram, it makes it easier to visualize what's happening. All right, for those of you who've been working on your homework before, both the textbook homework and the lab homework, does this kind of help out? One of the questions literally gives you the method on how to solve, one of the examples I gave you literally gives you the method on how to solve some of the questions in your lab homework. And if you haven't looked at it already, you'll figure it out pretty quick. Okay? Any questions from y'all? Cool. I got about 20 minutes till, so let's go ahead and call it a morning, and I will see you all tomorrow. Thank you, guys.